remain on mute unless they have something to share, but we are predominantly probably going to make use of the chat function and then invite people to talk. Just makes it for a cleaner experience. And this video will go up on YouTube on our channel at a later point. So we'll just give everyone the last few minutes and then we will get started. Okay. Lovely. Okay, so we're a few minutes after, so I think we'll make a start. Welcome everybody to July. And I can't believe it's July already, but July's Open Source Satellite monthly session. For those of you who have been to our sessions before, you'll probably be familiar with the format. For those of you who haven't, I'm going to quickly run over that now. So every month we get together and we're looking at promoting an open source kind of space community, and we like to get together and kind of share some ideas and talk about sort of different bits and pieces. And this month we're really excited to have some guest speakers who we'll come to in a moment. And yeah, that's what we're going to do. So hopefully we'll have a good sort of 45 minutes together. If there's any questions at any point, please throw them in the chat, and between us we will marshal those questions and give people the opportunity to ask any questions that they might have. So I say we are recording a session, so I could just ask you, please remain on mute unless I'm invited to come off mute, and we should hopefully get a nice run through. So I'm going to give a very quick overview because I think some names I recognise and some I don't. So bear with me for a few moments for those of you who already know what Open Source Satellite Programme is all about. But I wanted to just give everyone a quick overview so you can kind of understand the context of what we're doing and why we're running these sessions. My name is Vicky Hampson, and myself and some of my colleagues on the call here work for a company called KISS Space. And we're really passionate about trying to make space more accessible to a wider market and remove some of those barriers that stop people getting involved. But we're also really keen to do this in a sustainable and responsible way. And so what we want to do is develop a microsatellite platform that's robust and can be used for. Is you'd better go onto the internet and you'd be able to kind of get copies of the schematics, the software, everything that you would need to build your own satellite, but of a good quality, and that can satisfy a number of different missions. And on the screen now should be kind of a screen grab of some of our bits of our website where you can go on and find more information. And if you have any more questions on the open source satellite, I'm sorry, can I please just ask all microphones to be muted? Sorry. Thank you. If you have any more questions or would like to talk about the open source satellite specifically, Catherine, who is on labeled as Open Source Satellite Programme, or myself will be more than happy to answer those. Please just ping a message in the chat. I'm going to say there's lots of information on our website. Go check it out. You can also see our YouTube links to our previous videos and kind of other topics that we've talked about. And we've covered a whole wide range of topics and things. So that's who we are. That's why we're here. And we're really fortunate today to have some guest speakers. And they're going to talk about a topic which always excites everybody. Whenever I talk to people about space, everyone always is very excited about propulsion. It's a really interesting topic, and I think something that people has a lot of scrutiny on it over especially kind of around that responsible use of space and how do we make space use space in a responsible and sustainable way. So we're really pleased today to have a couple of people from Dawn Aerospace join us, and there's probably a few more hidden on the call that I can't see. But what I will do, say kind of butchering their introduction, I'm just going to hand over and I'll let you guys do your own introductions and talk about kind of propulsion and how we choose propulsion for space. So if it's okay, I will stop my screen share and I will hand over.
Perfect. Thank you so much for that, and thank you all for joining the call today. I'm Jeroen Wink, one of the co-founders of Dawn Aerospace and the Chief Revenue Officer. Now let me see if Vicky, can you confirm that? First, I would like to give a brief overview of what I'm going to talk today and of our company. So as Vicky indicated, the topic is on propulsion, and we're going to highlight multiple the various elements that are related to satellite propulsion and all the things to consider. If during the presentation there's any questions that come to mind, please put them in the chat. And then later, my colleague Josh, who is on the call as well, and myself will try to answer all of them as good as we can. So that's on the presentation. Then on Daan Aerospace, we are what we call space mobility company, and the mobility entails the journey of a satellite from Earth to space through means of our space plane that we're developing, but also satellites moving around in space once they are there from point A to B, and getting them out of space again later on. And that's what the other half of our company working on in-space propulsion works on, and that's also of course what this talk today will focus on. So we're currently with 75 people spread over 2 main sites in Christchurch, New Zealand, as well as here in Delft, the Netherlands. And then we have my colleague Josh, who is in the call, representing us as boots on the ground in the United States. On the satellite propulsion side, we currently have 33 thrusters in orbit right now on 8 different satellites, and thrusters currently on order and being rolled out to our various customers. Brief overview of some of the customers we can talk about. One is the Orbit, Italian company, but also very big in the UK, working on in-space mobility and space stacks. We deliver thrusters for them. Pixel, a very exciting company from India, making Earth observation constellation using hyperspectral imagery. LAPAN, State Space Agency of Indonesia, building a constellation of satellites for basically connecting all the sensors they have in their tsunami early warning system together, so they can get sensor feedback real time. So a wide spread of applications, and all of them need propulsion, and we're very happy that we can support them. So this talk will basically focus on what are the important things to consider when selecting a propulsion system, with a lot of typical points and questions that come up, like the performance, flight heritage, cost, etc. And also kind of try to weigh out what is the relative importance of them all. In our opinion, all of these aspects are very important, but what is even more important is the payload. Propulsion and all the components in the satellite bus, for that matter, should serve to cater to the needs of the payload and the mission, not the other way around. So in our opinion, bus components should be designed to be simple to use and easy to integrate, so that all mission rather than housekeeping of the bus. So with propulsion, the first question, or the first metric that people typically look at, is the performance, and specifically its specific impulse, also often shortened to ISP, which is basically a measure of the fuel efficiency of your propulsion system. So basically, how much fuel do you need to get a certain amount of thrust for a certain period of time? So ISP is the simplest metric to look at, but with that, some other aspects might easily be overlooked, and these include things as, okay, to get this specific impulse, to get this performance, how much power does your satellite actually need to generate and to give to this propulsion system to get the performance that is advertised? And also, with this efficiency, how long does it actually take from A to B, to get from A to B, to use more terrestrial analogy, going somewhere by foot or by bike will always be more fuel efficient than by car, whether it's gasoline or electric. But of course, it will also take you a fair amount of time extra to get to your destination, which might hinder your mission a lot. So it's very important to not just look at the fuel consumption, but all the elements that surround performance. And with that, it's also important to look forward at the trends. So high specific impulse, meaning a very low fuel consumption, is to keep the amount of the cost of getting, whether it's a kilo expressed per mass or per volume, whereas also ISP and quick can your satellite get to its destination, how much power do you actually need to give it, and can you perhaps give that power to your payload instead, and also can you have one propulsion system that can perform many different functions. So certain missions are simple enough, and you only need one thruster and that's it. But some other use cases might require 6 degrees of freedom control authority, and it can be advantageous when that can be provided by one propulsion system and not having to split up your delta V from attitude control, especially when you go to higher orbits where typically attitude control has to be assisted by propulsion. Then another important aspect, and especially when we look at initiatives like Open Satellite, where open source satellite many things and make things more modular and plug and play, is can you actually fit your propulsion system and any other bus component for that matter in your satellite. Different things to consider with propulsion systems, whether it's our green technology or whether it's a classic hydrogen and some electric propulsion technologies. They all require a fluid, a gas or a liquid, to be stored under pressure. And when you store something under pressure, you need to store it in a tank or a pressure vessel. And ideally, you don't make this rectangular or a cube, because that will not be a very efficient structure to hold that pressure. So what we often see when we do an early study with a customer is that based on the performance metrics, they come to the conclusion, we need so many liters of propellant, so we will accommodate so many liters in the satellite for it. But it's not just the amount, but the shape matters. So this needs to be kept in mind, and it's advisable that as early as possible you discuss with your propulsion supplier of choice what is the volume they need to stay in. So a lot of microsatellites, for example, they will have something like a separation ring. And this separation ring actually to connect and later separate the satellite to the launch vehicle. And the separation rings often have some mechanism on the inside. So it looks like you have a lot of volume, but suddenly there is a cutout, which by itself doesn't look like a big thing, but it's very problematic if this cutout has to go through a high pressure tank. So suddenly things might become a whole lot more complicated, or you get a whole lot less performance out of your system than you initially volume, but also what form factor does this volume need to adhere to. And also to make things flexible, it is our vision that it's important and useful to, as much as possible, standardize the interfaces, but not the form factor, because each mission will be driven by the payload. Something that has, for example, a big telescope, for example, in the satellite will have very different requirements than let's say a low bandwidth communication mission with a patch antenna on the outside. So there's not so much sense into standardize the form factor, but to standardize the interfaces so that different geometries of tanks or different architectures of the and layouts of the feed system can easily be changed without having to make changes at a higher level, like on the control software. So that's also why in our approach we deliver turnkey systems complete with control electronics and control software. And these interfaces, they are standard whether we talk about a tiny CubeSat module or a propulsion system that has the size of myself. We try to keep that as standard as possible, and it's our advice that you look for this elsewhere as well. Another trend we see that is very relevant when looking at propulsion is basically the life cycle of space projects and of satellites. So where in the past the development of a satellite had to be booked years in advance, this is all coming down. So now we see an increasing amount of users making use of, for example, the SpaceX rideshare program, where sometimes in less than 9 months before the launch, the launch contract is signed, and that really squeezes the development timeline together. So with this, in order to make this possible and to accommodate this higher speed that the commercial market needs, it's very important to look at lead times and also what are the risks associated in these lead times. So look into what technology is used. Are certain like exotic materials used that are hard to get by, are hard to machine, so are prone to cost delay? How easy will it be to integrate the propulsion system into your satellite? Looking back also on my earlier statement on trying to keep the interface as standard as possible and at high level as possible to make this integration quick and easy. Go for systems with a limited part count, because every typical on a satellite there is very little components that are not critical. So each individual part is in fact on the critical path. So keeping the part count low will reduce your risk there. And also how surprising it might sound, look at can you actually get your propellant on the launch site on time, and also what implications will your propulsion system have on this whole process on the launch site. So certain technologies system to you pre-fueled, so you don't have to do anything at the launch site with it, whereas other technologies definitely need to be fueled on the launch site, where on the opposite extreme of the spectrum you have classic hydrogen systems that are very hazardous operations. They need to evacuate a big part of the launch site when that takes place. So in those cases that really starts to drive your operation. And it's very important that you know in advance what to expect and what not to expect. Then something the iteration cycles of satellite and spacecraft development get shorter. It becomes very important that you it is always very important to fly what you test and test what you fly. And to make that as easy as possible. So look critically at how much can you test the hardware before you launch it, and it's not just the propulsion hardware, but the whole chain that is needed. So one thing that we typically support customers with is that they actuate, so they test the propulsion system we built for them with their own satellite avionics. So it's really testing what you fly, so that you can fly what you have tested. And making this as easy as possible is a great help in de-risking the mission, especially when there's a lot of new things in the mission and the schedule is challenging. Some other technologies are also very suitable. Extremely difficult, if not impossible, to test properly on the ground. So these are things to keep in mind and discuss quite far in advance with your proposed suppliers to see what is possible in this testing phase and also what is impossible there. Then an element that is often overlooked is what about the propellant itself? Because propulsion system is not just the hardware and software that you buy from the manufacturer, but it also needs its propellants in there. There have been examples in the past where a satellite was ready, its propulsion system was ready, everything was ready to launch, but they couldn't get the propellant they needed on the launch site in time. So launches were delayed for 6 months simply because they couldn't fuel the tank. And this is, of course, very frustrating for all the parties involved. So look ahead at what all is needed at the launch site itself. Can you get the propellants locally, or do they need to be imported? If they need to be imported, what are shipping times? Do you need to look into import and export restrictions there? Also, is the propellant you use something that is, say, widely spread in industry and has many different use cases apart from propulsion, or is it a very niche or even proprietary product which comes with all the associated lead time risks when there's only a single supplier that can deliver this? This, despite it being often overlooked, it's our strong recommendation to look at logistics as early as possible, as that can be an unfortunate surprise for some if this hasn't been taken into account. It's also one of the reasons why we design all our systems to use nitrous oxide and propene. So they are technical grade propellants, widely used in industry. So pretty much any launch site you can think of, there will be a handful of domestic suppliers who can deliver it locally to simplify the logistics around this. Then propulsion, perhaps more than most other bus components, is subject to many rules and regulations from all kind of stakeholders other than just your own customer or yourself. So typically the launch provider and also the operator of the launch range, which are often not the same entities, they look very critically at anything that has a propulsion system on there, because in general propulsion will have high pressure systems. It might have flammable or corrosive or oxidizing or otherwise interesting fluids on board. So it's something that is looked very critically at by launch providers. And these are discussions to have as soon as possible, as these are kind of third-party stakeholders that, even though they are a third party and they only typically come into view quite far into the process, they actually can veto things. Everything regarding the important look at these things early. And way is SpaceX with their transporter rideshare program, which increasing amount of the micro small sat market is using as its ride to space. They recently in June this year updated their user manual. And they added a whole new section on pressure vessels, which was not there to begin with. And so they came with new requirements and basically forbidding certain types of tanks that from a propulsion point of view are very attractive because they're very lightweight, high performance. But if these type of tanks are used, your propulsion system looks extremely attractive on paper because it will be very lightweight and very high performance. But it cannot be launched anymore with SpaceX, which is one of the most popular ways now to go into to orbit. So look at this from an early stage and also talk critically with the suppliers you're talking to. Do they confirm if regulations, and also how robust do they think they are against regulations that might change or new things that are introduced, like the pressure vessel example here from SpaceX. And this is true for the design, but also for the operations on the launch site itself. So what is involved in fueling your satellite on the launch site? The launch provider and the range authorities, they will have to review and accept the procedures you're using to fuel the satellite, and they can veto this and hence block your launch if they're not happy about something. So try as early as possible in the process to get your preferred provider for the launch service and your preferred provider of your propulsion at the same table, or at least on the same call, to start aligning on these matters as soon as possible. Then another question that often comes up, especially early in, let's say, component selection and early in the design process, is the flight heritage of a certain technology. This is very and this has a number of interesting elements. So at the one hand, it's important to realize that having launched something in space does not automatically mean it worked in space. So it's very important to verify, do things actually work? At the same time, especially in the more traditional part of the industry, satellite operators rarely share data of the components to their lower tier suppliers. So it's very difficult sometimes to get on orbit data of your thruster, or well, the thruster of your supplier, of how it behaved in orbit. As I said, operators very rarely share data when things go well. They typically only share things when an anomaly occurs. Luckily, with propulsion, there are external ways to validate this by tracking the orbital elements of the technologies. You can externally validate, do these satellites in fact move around, or are they indeed stabilizing their orbit instead of decaying? So with this, you have a nice and external way to validate some of the flight heritage that for other bus components is not so straightforward to get this validation externally. So that's a recommendation we would give anyone, is verify the functionality of what is already in space externally by trying to track the satellites. And then a final element to consider is basically related to the summary of everything I just discussed, is that with propulsion there's a lot of external matters to take into account that are often not not straightforward for you as a builder of the satellite. So really critically assess if the supplier you want to select, if they are willing and able to help you with all these matters. Do they raise with you in advance certain things about operation on the launch site, or do they have a plan already in mind, and do they communicate it to you how you can get your satellite fueled prior to launch? And are they do they pick up proactively with you, and also when are they willing to engage? So yes, it's very important, I would say, to view all these matters holistically and do that as early in your design process as possible, because then things are typically still quite flexible and making a change is easy. The further you are, the closer you are to launch, the more painful and difficult, and sometimes even impossible it is to make changes that a third-party stakeholder might impose on you. So yeah, look for a technology that first of all is robust against this, but also look for a provider or a supplier that is proactive and willing to support you with all these matters. So that concludes the topics I wanted to address. So with that, I guess we can open the floor to the questions and answers, and maybe with a final remark that Josh and myself, together with some other people of the team, we will be at the SmallSat conference in a few weeks in Logan, Utah. So if any of you want to follow up in person, just send us a message via this email, or scan the QR code to directly put something in Josh's calendar. And we're looking forward to see you there in person. With that, I want to open the floor to question and answer. So I guess, Josh, you will review the questions and we'll go through them.
Yeah, I can't see any questions coming through from the chat. So maybe we just open it up, and if someone has a question, unmute themselves and fire it away. And I'd encourage everyone not to be shy.
Is that someone with a question? Put your virtual hand up too, and we can also go around. I just wanted to quickly say that was a really interesting talk, and it pains me sometimes because I'm a platform designer, and I like the fact that you put the payload front and center. And I think sometimes we when we all do our widgets and our bits, we kind of always forget actually people aren't always that's not the bit that makes gets the data, makes the money, all that bit, but it's really important. But we are all there effectively as a service to this payload, whether it be image taking or kind of data collection and the like. And it was really interesting to see that bullet list, and actually performance was just one of such a long list of different things to think about. And a lot of those things, if you didn't catch up front, the amount of money that you could spend, right, putting that right, or just having your launch vetoed, right, that would just be the worst case scenario, because you've put all that time and effort and things in. So I think they were really interesting points, and definitely things I think Catherine and I will definitely be taking away to think about. But it does look like we had a question. Josh, I'll let you cover that one.
Yeah, why not? Any specific concerns for monopropellant and electric thrusters?
Yeah, I would say so. For full disclosure, we do neither of those. So perhaps my answer will be a bit biased. So just keep that in mind. For monopropellant thrusters, I think two important aspects should be looked at. One is that monopropellants, they typically have some operational constraints. So they have a 9 out of 10 will have a catalyst bed that decomposes the monopropellant into hot gases to make to generate the thrust. And this catalyst pack is hydrogen, like classic thrusters, the propellant, sorry, the catalyst can be poisoned by CO2, hence by ambient air. So it will be a very sensitive thruster to handle on the ground. Whereas some of the green monopropellants, they require a catalyst that the catalyst pack will only work when they're heated to very high temperatures. So this will introduce a operational constraint, this time not on the ground, but in space, because when you want to use your thruster, you actually should already start firing it up half an hour before, just to make sure that your engine is warm. There are some operational things to consider. And then, yeah, monopropellants are typically also energetic materials. The same is true for example, the nitrous oxide that we use as oxidizer. So there are some safety concerns there that need to be addressed properly. Yeah, electric in general. What's very nice about electric systems is that they have a very high specific impulse. So you need a very small amount of propellant to get from A to B. And definitely for missions that want to go far out. So let's say interplanetary missions, it's typically the way to go, just because you can put so much delta V in a small, so much impulse in a small volume. But it also has drawbacks on very high power consumption and very low thrust generation. So you can go really far, but it will also take you a very long time to get there. So there, the main consideration should be in looking at your operations in space and like how often and how long. Hence, how long can you? Certain missions, it makes a lot of sense to go electric because it keeps everything small. For other cases, it might make more sense to go for a system that doesn't require so much power and gets you from A to B a lot quicker.
I was muted. Cool. Next question here, propulsion systems. Oh, hang on, there's one before that. Can you tell us something related to thrusters which use water as the propellant? Is there anything to be kept in mind before testing or designing them? And maybe we can talk a little bit about like resistor jets are typically quite low cost, but there are costs in other areas that you need to take into account.
Yeah. So water as propellant can be used in, say, different ways. The most straightforward one is indeed as a resistor jet. So you have some water, you put it under pressure to flow it to a thruster. In that thruster, there is a big heating element, and it turns the water into hot steam and generates thrust by that. That's the simplest way. It's indeed very simple and low cost, but falls somewhere in between the spectrum of chemical and electric. So it's still quite high power consumption for not that much performance, but it's very attractive that it's can be kept quite simple. And water is also nice that it's a dense propellant, so you can keep things nice and compact. Another way water is now proposed, another way of using water as propellant that is now proposed is to actually separate the water into oxygen and hydrogen on board of your spacecraft. So you store it as water, which is nice and dense and safe to handle and non-toxic and etc., non-pressurized. And then you separate it into oxygen and water while in space, and then you actually combust the hydrogen and the oxygen. So that's then you get a very high performance, like very high specific impulse, because it's hydrogen oxygen that you combust. So you combine relative simplicity, even still quite high performance. There it is. How do you actually require, for example, that you need to spin up your satellite before you fire the thruster to like separate the oxygen and hydrogen from each other by centrifugal forces? So that's fair enough way to do it, but it does introduce new operational constraints on your concept of operations.
And probably a smudgy picture.
you want to touch a little bit on maybe the increase in launch costs if you want to chemical, but to get the performance and the amount of propellant that you need, additional launch costs are going to increase.
Yeah, so that is indeed true. Quite some amount. Very small satellites, typically your launch costs are driven by volume rather by the mass, and then since water is quite dense, doesn't require, so it's not really an issue there. But for larger satellites and larger Delta V budgets, that water starts to become heavy real soon. And for larger satellites, your launch costs are driven by mass rather than volume. So then, yeah, you can save quite some money on your propulsion hardware by using relative simple technology. But then if you pay, 5,000 per kilo with SpaceX and many times that per kilo with other launch providers, then each extra kilo of water you need to bring on board will quite quickly offset any savings you made on hardware.
Next question from Tom. Propulsion systems are often mission critical. How do you balance when looking at different suppliers?
I would say what is the most important because of indeed its mission criticality is its reliability, and like heritage is one way to assess it, but other things like looking at what is the complexity of the system, how well is it validated on the ground already, how easy is it to test, can you test the entire chain from like up to the onboard computer of your satellite down to your thruster, be it chemical or electric or otherwise generating thrust. Can you test that all on the ground? Heritage, so I would be it would be attractive for me to start pushing harder for no, just look at flight heritage, because that's after years of being a struggling startup, we finally find ourselves in a comfortable position here, but it's really not the only thing to look at.
Do you want to give some tips or tricks on what we did prior to heritage?
Basically the things I mentioned, trying to design things to be as simple as possible. If the component isn't there, it cannot fail. To name our specific examples, we selected a technology that is self-pressurizing. So where with many chemical propulsion systems, you would need a separate helium tank and then a very high pressure regulator to regulate that high pressure helium down to a lower pressure that goes into your propellant tank. These are very, especially the regulator, complex and failure prone components. And if you don't need them, they also cannot fail. So designed for simplicity and designed for testability, so that high configuration as possible to de-risk things on the ground as much as possible.
And I think that kind of ethos and the mentality also transfers across into the platform, right? Because you could have a thruster with the prop system, the most heritage ever, but if everything that sits behind it isn't very good, that doesn't matter. I think it's that looking at that big architecture piece as well, right? Like what you have sitting behind it, how you do that control, and how robust the rest of your system is as well. And it's definitely something that we're advocating as part of the open source satellite. Looking at how we do that robust architecture. It's not always a case of just putting everything on. That doesn't always solve your problems. But it's looking at how you make all that hang together. And it's an interesting topic, and it's something that we wrestle with a lot, because as we've talked about, every time you add something extra in, it costs a bit more because it's heavier. You're buying more bits, and you kind of can introduce some reliability issues. So it's a really good question, and it's an interesting one to solve, isn't it? So
and especially with propulsion, like when you look at electric propulsion, it's a lot of power that is required. But even with chemical, like the power consumption will be low, but likely you have a brief period of a very high current that needs to be provided. And yeah, this system can be the best thing ever when supplied with a nice power supply in the lab. But it might turn out that once you activate all the loads on the actual platform, that maybe the amount of current that's delivered is just undershooting what it should, and then the valve doesn't open. So yeah, look at the whole system and test the whole system. Test at system level is a big recommendation.
Another question here. What are the technical safety, and maybe we can just talk about energy.
Yeah, so a few important things are test for leak tightness before you load actual propellant. So and make sure that after you test it, that everything is leak tight. You don't change anything anymore. That final leak test should be the last thing you do before you load propellants. So that's a very important thing. Yeah, obviously know what you're fueling it with. So our propellants, they are very benign, they're green, so non-toxic, so they're reasonably straightforward to handle, but nonetheless, the fuel is flammable. The oxidizer, if they are under reasonably high propellant, should always be treated with respect, no matter how green or non-toxic it might be. So know what you're using. Make sure that you treat it in the proper way. Make sure that all the materials you use are compatible, like all the metals in your propulsion system, all the let's call them rubbers, like the soft materials for seals and whatnot. Make sure that they are you might have a very dangerous propellant like or in our case nitrous oxide. Titanium, the material safety data sheet probably, and make sure that your procedures are compliant with those things as well.
Cool.
And perhaps the last element for safety, always assume it will go wrong and design your procedures around that. So when you have a large propellant tank, assume that something might rupture, and hence make sure that you're not standing next to it when something active is flowing. Like assume it goes wrong and base and procedures around that scenario, because then you're at least safe and robust against failure.
We talked about the necessity of not having a fancy fuel oxidizer because of lower availability. But as market research goes on and your propellants with high performances are tested, doesn't it make sense to use a new type of less available propellants, a possible gain that could be obtained? What is the level of risk you accept when evaluating a different type of propellant?
I mean, this risk is not for us as a supplier to accept, but more a consideration for whoever wants to operate but it's very nice. You can get a performance boost using something very exotic or fancy, or like some lab grade material, but nothing more at the very different, but I would say for most commercial applications, focus on what is available in industry and not so much on what requires a single lab somewhere in the world, and require that lab to scale up at some point.
I think this also comes back with the requirement.
Perhaps on mixed oxides of nitrogen as the oxidizer instead of the normal nitrogen tetroxide, and basically they changed the mixture to have more of these smaller molecules in there. Because its freezing point is a lot needed for, let's say, a few Mars landers and these Mars sample return scenarios. So from a cost or a logistics perspective, it completely doesn't make sense to go in there, like to go into that direction. But the use case of like having to survive for a long time on the cold surface of Mars, yeah, that definitely makes it worth it. So there are definitely some scenarios where my rule of thumb doesn't apply to. And yeah, science and exploration typically will cover such scenarios.
Maybe we talk a little bit more about premix propellants as well. Have you got any comments on those?
Yeah, well, of course I'm biased because we don't use it, but I would say stay away from it. So premix propellant, you make a flame or you can let something explode by mixing something that is a fuel, so that can burn, with something that's an oxidizer. We store them separate, and most people store them separate, and they are only combined in the engine themselves. So let's say the risk for explosion is only there in the rocket engine where you want it to happen. If you want to, let's say, simplify your system by only having one tank instead of two, you can also pre-mix them. Then you get the same amount of performance, but now your system is a lot simpler. So something that looks very attractive, but well, I don't want to be the test engineer that test fires these thrusters. I don't want to be the guy who loads up the satellite when fuel and oxidizer are already pre-mixed. Luckily, right now my role is purely commercial, so I'm not doing the technical work anymore. But nonetheless, I wouldn't want to do it to any of my teammates. My advice is to stay away from them. Again, I'm biased because we don't use the
considerations that we make to withstand harsh conditions in space.
Yeah, so harsh conditions, of course, has many elements. One is already the ride to space, so the harsh vibration and shock environment that the satellite is subjected to in the launcher. So there, simplicity for us is key. So by taking away a lot of complicated mechanical things like pressure regulators or mechanical propellant management devices, we take away basically everything that is prone to damage by these mechanical loads. So that makes things a lot simpler. That's for us in general. It's make sure it's tested. Whatever you propose, make sure that proper environmental qualification is performed, and that encompasses vibration, shock, thermal vacuum. When there's electronics involved, also make sure that its sensitivity to cosmic radiation is well understood, and that it in fact survives that. So yeah, consideration design is make it as simple as possible, because anything that is sensitive to failure that you can skip can then not fail. And for anything that still needs to be on there, make sure it's duly tested.
Lovely. I think that brings the questions to a close. I don't know whether either of our colleagues here from Dawn wanted to make any final comments before I do the wash up and close out.
The final comment basically similar to the and inviting us and the whole audience for making the time available to listen to my mumbling, and also as said earlier, we will be at the SmallSat conference in a few weeks. So if any of you guys and girls intend to be there, send us a message, and it would be great to present. And additionally, if there is follow-up questions that we didn't get to in the Q&A, our contact details are in the presentation. So you're very welcome to reach out, and we will engage with you. So
I've also put my email into the chat, and also the link to the calendar booking for SmallSat.
Awesome. Well, thank you guys so much. I mean, I've learned lots, so it's been really super useful, and it's there's been some really interesting points to sort of take away, and it's nice to see that some of the parallels between kind of the propulsion world and some of the platform world, and actually how we all face a lot of the same sort of challenges. But no, that was really super. So thank you so much. I really appreciate you giving up your time and coming to talk to us today. And as I say, I think everyone will virtually say thank you, because it really was great. So thank you very much. So just a quick wash up now. So I say obviously the Dawn guys are giving their details. If you're interested in finding out a little bit more about what we're doing in kind of the open source satellite domain, or kind of this kind of open source space ecosystem that we're trying to kind of grow and promote, then do get in contact with us as well. We really want to kind of promote kind of a sharing of space, that to get away from some of these silos, and kind of actually foster an environment of discussion and information sharing. And so as part of the open source satellite program, there's lots of information on our website. And if you see things which are of interest, or you've heard things today that are of interest, drop us a line. We'd love to hear from you. So we have a whole range of different projects and aspects going, realize this vision that we and so if any of the things on screen at the moment, take your fancy, then give us a shout and say we're looking at getting this out here soon, and using it as a real a real thing, and get some missions up. We are having a break in August, so we normally do these monthly, but there will be a break. We're having summer holidays, because we figure most people will probably be away in August if people haven't already started on their summer breaks. And we will be returning in September. We will put out the date and topic soon. We will also be putting out a link to this recording, which will go up on YouTube. You can watch it again at your leisure and see all the wonderful advice that we've been given today. So that'll be great. And if you're sat there going, oh, actually, you know what, I've got a topic I'd like to discuss, or I've got a topic that I'd like you guys to discuss, then drop us a line. We really want to make these sessions kind of useful and interesting, and that's our whole kind of ethos around here. So if you think, oh, hey, I'd love to give a topic, a discussion or a presentation on a particular area, let us know. Or if you go like, hey, we'd really like some more about this, do you know some people? We probably do know some people. We're pretty good at tracking people down. It's just like the Dawn guys, who very graciously supported us today. So yeah, if you have any thoughts, questions, comments, or want to get involved, please just drop us a line. I must say, just to finish with, once again, thank you so much, and thank you everyone for your time, and I hope you all have a lovely rest of the day, or depending on what part of the day that you're in. So thank you very much, everybody, and we'll speak to you all soon, hopefully. Thank you. Bye.